Thank you very much. So first of all, thank you very much for the invitation to come here to the beautiful city of Florence and the beautiful institute. It's been an absolute pleasure. So thank you very much. So as Doreen said, I'll tell you some of the recent news on sector decomposition and some of the applications that we've been using this procedure for. And this work that I will present is in collaboration with the PySecDec, my collaborators within PySecDec, who are shown here squinting in the February sun at Karlsruhe. They're excellent postdocs and PhD students, and they're responsible for a lot of the development that I'll present here today. And I'll loosely base it on these papers that I list here. And some of them are written also with other members of the audience, Yinan, Franz, Yao, etc. And some older work with our previous members of the PySecDec collaboration. Okay, so why should we be interested in sector decomposition? Well, it's a means for computing Feynman integrals. And as I think we all know, Feynman integrals can be difficult to compute analytically. And so there are various methods to try to approximate or evaluate them numerically. And this can be very useful if it's too difficult to get an analytic result. Some of the methods include numerical solutions of differential equations, series solutions of differential equations, and there are several packages, public packages that implement this idea. Mellon-Barnes or numerical Mellon-Barnes, again, there are public packages for this idea. Taylor expansion in the Feynman parameters. A slightly newer idea is this tropical sampling, FineTrop, and there's a public package for that. Numerical loop tree duality, and we'll hear from one of the collaborations working on this tomorrow in the talk of Dario. And then, of course, sector decomposition. And of course, there are many authors that have worked on these packages and on the idea behind these packages, but I just list the public packages here to give you an idea of the amount of work and the scale and the different approaches. Okay, so since I'm going to talk to you for half an hour about sector decomposition, I'm going to try to introduce it as briefly as possible so that we're all clear on the idea. And I'll try to introduce it from a perspective that will be a little bit useful later. So what is sector decomposition? Well, we have objects like this, Feynman integrals. And here we've Feynman parameterized it and done the momentum integration and expressed it as some remaining integrals over Feynman parameters. And we can write it something like this schematically, where these x's are the Feynman parameters that we want to integrate over, s are some Mandelstam invariants, kinematic invariants, and then we have an I delta here. And what's the problem with just numerically evaluating this? Well, primarily it's because it has singularities. So it can have UV or IR singularities when some subsets of the Feynman parameters go to 0 simultaneously. And so we would like to isolate these singularities and have some procedure for dealing with them. And one way to isolate them is sector decomposition. So this is essentially what this is used for. And then, of course, we can have thresholds when the F polynomial vanishes inside the integration region. And we try to deform our integrand around these via this I delta prescription. So in short, sector decomposition is a local change of coordinates for each singularity that factorizes it, which is closely related to blowups in the mathematical literature. So this is the goal of sector decomposition. Okay, so how do you actually achieve a sector decomposition? And here I give the geometrical perspective on this, thanks to Kaneko and Ueda, which I think is really helpful later on. So we can view a Feynman integral or a general integral actually of a certain class like this, where we could in principle have a product here over this over these polynomials. We could have more than one polynomial multiplied together here in general. Okay. And the geometric method, what you do, you have your integral over the Feynman parameters. And here you have some implicit sum over I. So this is some polynomial with monomials that look like some Ci times some x's to some powers. And the powers of those x's we call Ri. So we can view each monomial in our polynomial as some point in the exponent space defined by this vector Ri. And now there is an object called the Newton polytope that's extremely useful. It's defined as the convex hull of these points in the exponent space. So you read off the exponents of your polynomial. Each monomial gives you a point in the space. You take the convex hull of that, and this is your Newton polytope. And this Newton polytope, as well as having this vertex representation, it also has a facet representation. So you can instead see it as the intersection of half spaces. And this will define the same polytope as defined by these vertices here. This is useful because the normal vectors incident to each extremal vertex define us a local change of variables that will give us the singularities in a factorized form. This means that once we have the facet representation of our Newton polytope, there is some change of variables that just depends on the normal of these facets, NF. We make this change of variables, and we can rewrite our integral as having these singularities factorized out. So now we have integration over these new variables, y. The singularities sit out the front. And then here we just have a polynomial that we are sure doesn't have any singularities when subsets of these y's go to 0. There's one slight complication, which I won't really go into, but in general, you could have a situation where you have more rays of one of these, more facets incident to an extremal vertex than you actually want. Essentially, you get more facets incident than you have dimensions, and then you need some sort of triangulation to define linearly independent variables. It's a technicality, and it can be dealt with. I think an example probably makes this much clearer than anything I just said. You have an integral. It has some polynomial. You can read off the powers of these monomials, and they each define a point in the space. So here, just 1, 0, 1, 1, 0, 1, point in the space. Your Newton polytope is the convex hull of these points, R1, 2, and 3. It can also be defined by just these normal vectors here, these half spaces, intersection of half spaces. These normal vectors give you exactly a change of variables that will factorize the singularities. So they sit out front and then give you a polynomial here that when you integrate out each of these deltas, this will not vanish anywhere on the boundary for the y's going to 0. So this is just the idea. So this viewpoint will come in helpful later. Okay, so what are the type of problems that we would like to attack with this? Well, we would like to try and get out to the forefront. So sort of one frontier that I would say is sort of partly conquered by this point is two-loop 2 to 2. And this is essentially fine. Sector decomposition works well here. We computed di-Higgs, Higgs-jet, ZZ, Z-Higgs here with internal masses, etc. And sector decomposition is completely up to this task. We could then ask about adding more masses into this problem. So we could consider, say, two-loop electroweak corrections. Now we have many more masses potentially in this problem. And I would argue that sector decomposition could be a suitable tool there because these masses generally don't make the sector decomposition significantly harder. We could have situations where we have large hierarchies. So for example, we have a small mass or a large invariant somewhere. And here, something like an expansion, like the method of regions, turns out to be useful and may be able to make sector decomposition, again, usable in this sort of scenario. And then, of course, we have 2 to 3 at 2-loop, which is very challenging because of the high dimensionality of the phase space. So we have processes like this, for example, and then 3-loop and beyond. One thing I'd like to say is that in the context of adding masses, I'm actually involved in a project with my PhD student, Tom Stone, and the group of Gudrun Heinrich, computing this type of diagram with sector decomposition and with other methods. And I'll say a little bit more about this process later. Okay, in order to attack these problems, we need to improve our algorithms or find ways of speeding up sector decomposition. Ultimately, it's a numerical method, and you're limited by the computing time. So you need to be smart with how you use it. So there are several opportunities here to improve. We can improve the algorithm and the implementation. We can try to find smarter numerical integration routines to numerically compute these integrals. We can think about better ways of deforming our contour. And then, of course, we could make use of expansions when we have these large hierarchies. So let me start by telling you some of the changes that have happened over the last 2 years in PySecDec. The last version, we implemented a full adaptive sampling of sectors. This means that we don't throw the same number of points into each sector, but we actually adapt the number of points in each sector based on its total contribution to the error. We also worked a little bit on finding better contours, or essentially adjusting our contour if need be. We then worked hard on many optimizations in the integrand code. These are basically technical points that I won't go into. In the new version, we implemented a new quasi-Monte Carlo integrator that we've dubbed Distaval if you use our code. And it's a faster implementation of the old integrator, but it has some quite smart changes, I would say, primarily due to Vitali. So it has a fusion of the integration and integrand code. And this means that when you're generating the quasi-Monte Carlo lattices that we use for our numerical integration, you do less modular arithmetic. Modular arithmetic on a graphics card is slow, so this is really helpful. We have better utilization of CPU instructions, and then we'll also have less synchronization between our GPU and CPU. So we sum our results on the GPU directly and then just send the result back. One feature that I think is useful for our users is that we can actually pass amplitude coefficients with GINEC now, so we can support partial fractioned input and so on. Previously, we forced the way you input your coefficients to be very particular form, and this was annoying, I think, for everyone. And of course, this can be distributed on several machines. So does it help? More importantly, the answer is yes, it helps a lot. So if we just take an example integral like this, and these are the different versions of PySecDec. And this is the time in hours to compute, say, on a GPU or on all the threads of your CPU. You can see that we went from greater than 2 days in version 1.4 down to less than half an hour in version 1.6. So this is a lot of improvement. And to give you some idea, if you know the calculations we've been doing, Higgs would have been done with performance that's somewhere between 1.4 and 1.5. So you can get an idea of the type of process that we would be able to calculate with the improved code just from that. Okay, so let's try profiling it. Here we take an example from TTH in 6 dimensions. And here we have the integration time and the requested precision. And what you see is that the time is essentially less everywhere on this Distaval. So we basically reach any given precision quicker with Distaval than we would have with our old code. And to give you some idea on a GPU, the speed up going from our old code to Distaval is about a factor of 5 for this integral. And on CPU, it can be a little bit more. This gives you an idea of the timings. We can do the same thing for 3-loop integrals, but at lower point. And again, we can see that many of these integrals are computable in sort of seconds to minutes per integral to achieve a practical precision, depending on how you define that, but give you an idea there. Okay, cool. So the second topic is how we actually do the integration and the integration algorithm itself. And here we've changed how we generate our lattices to use so-called median lattice rules. Let me explain to you why we did that. And I'll start by telling you what a lattice rule is at all, in case you're not familiar with it. So rather than sampling in the space completely randomly, like Monte Carlo, what you instead do is you pre-compute, usually, a generating vector. You take this vector, you start from some point in your space, and the vector tells you how to generate all of the other points in your space, according to this formula here. So it generates some lattice in the space. And what we did was we would pre-compute this generating vector using a construction from some mathematicians called the component-by-component construction. And what was nice is that for a good choice of this generating vector, you can guarantee that the error of your numerical integration will scale like 1/n to the alpha, where your integral is square integrable and periodic, and so are its alpha derivatives. So, first, second, third derivative. And this is very useful because Monte Carlo scales like 1/√n. It's very slow scaling. You can accelerate this greatly by using these lattice rules for integrals that are square integrable in this way and periodic. The annoying thing about these lattices is that this component by component construction requires a large amount of memory. So on a 2 terabyte machine, we're limited to lattices of about this size. And you can also encounter what we call unlucky lattices. And I'll show you an example of that next. So what's the problem with these unlucky lattices? So here I show you the lattice size and the relative error that we get. So we sample our integrand on this lattice, and we get some estimate of the integration error, essentially. And this is some particular integral, and it's some particular sector in our sector decomposition of this integral. And what we see is we have a reasonable asymptotic scaling. So it's like n to the 1.5 if you fit a curve to this roughly, although it's a bit not really a straight line. Okay. But what's very annoying is that for certain lattices, you can have a lattice, say, of just bigger than 10 to the 9, and you have quite a small integration error. You go to a slightly larger lattice, which in principle should reduce your integration error, but instead you have an enormous increase in the integration error. So you have this kind of situation where there's large fluctuations in how precise your result is, depending on the lattice that you're sampling on. And this is not consistent across sectors. So if we go to a different sector of the same integral with the same lattice, it's fine. It behaves exactly as it should. So these lattices seem to not play well with every possible integrand. And we don't have a clear idea why that is. However, there is another way of generating vectors. And this is what we're actually using now in version 1.6 of PySecDec. So the idea is to use a so-called median lattice rule. It's a very, very simple procedure. You compute the generating vector on the fly for the integrand that you're considering. How do you do it? You choose a random R in this uniform range where n is the size of your lattice. You estimate the integral on each of the lattices. So you have R random lattices. You estimate your integral on each lattice. And then you choose a lattice with the median integral value. And then with this lattice, you can sample your integral a lot more to get an idea of your relative error. It sounds like magic, but it was actually shown in 2022 by these mathematicians here that, again, for an integral that's square integrable and its derivatives are square integrable and periodic with degree alpha, then the integration error indeed scales like 1/n to the alpha with a high probability, which depends on the number of lattice candidates that you actually try. So here I show you an example of this. We have 11 candidate lattices. For each point here, we generate 11 candidate lattices, and then we pick the median one. And what you see is there are still fluctuations, but a lot of these very large fluctuations that we commonly saw at very large lattice sizes seem to be removed by picking the lattice specifically for the integrand that you have at hand using this like adaptive median lattice rule construction. Okay. We have other optimizations to do with the contour deformation, and I'll cover this very quickly just in the interest of time. So the contour deformation tells us that we need to avoid poles on our real axis, and the Feynman prescription tells us the sign of the F polynomial that will allow us to do this. And I mean, thanks to the authors, some of whom are in the audience here, Davison, for example, we're actually able to come up with a particular deformation here that we can implement that will give us the correct sign of I delta. And essentially you have some deformation that has some small parameter lambda that is set such that you don't cross any poles. And for small enough lambda, this deformation will give you the correct sign of your F polynomial. And our idea was to start with this method that works well, which is what's implemented in PySecDec, and then try to generalize these small parameters. So rather than just taking a constant here for the small parameter, instead allow it to depend on the Feynman parameters itself, so that you have a more more flexibility in your contour deformation, and then you try to optimize such that you get a lower integration error. And to do this, to pick a suitable function, we tried using neural networks with Ramon Winterhalter, neural networks, in particular, normalizing flows to pick the contour. So the idea, roughly, is that these normalizing flows consist of a series of trainable mappings, which we can efficiently compute the Jacobian for, which is exactly what we need if we're going to use this as a change of variables. You try to train these normalizing flows such that you minimize your Monte Carlo error whilst still not crossing poles of your integration. And just to flash you a result, you can see that for some integrals, this can give you maybe an order of magnitude speed up. So for the same integration time, you can bring down your integration error by about an order of magnitude. So this is, I would say, a proof principle that you can use machine learning to find improved contours and reduce the variable. But there is definitely a trade-off between the training time and the integration time. Okay, this brings me to expansion by regions. And here, there is a well-known method. Again, many of the authors of this method are in the audience here, well, one in particular. And so the idea of this method of regions is a way of expanding an integrand about some limit. So the issue fundamentally is that integration and series expansion do not commute. So you'd like to find a way to expand your integrand and then integrate rather than the other way around. And this method of regions is a procedure for doing that. Essentially, you split your integrand up into several regions. You series expand each region in your small parameter lambda, and then you integrate each expansion over the whole integration domain. You discard the scaleless integrals, and you sum over all of the regions. How do you find these regions? Well, again, the Newton polytope is an incredibly useful tool for doing so. You go back to your integral, and here, some of your CIs will scale like lambda. So these are some external kinematic invariants that you want to be small. So you can say that you pull out the lambda from each of these CIs, or to write it another way, CI goes to CI times lambda. You then take as your exponent vector, not just the exponents of x, but also the exponents of lambda that you get. And this will give you a Newton polytope. And the Newton polytope will be in one higher dimension than before because it has this extra component in the lambda direction. And then the normal vectors that point in the positive lambda direction define a change of variables that will give you your regions. So this change of variables will give you your regions. So again, if we have some Newton polytope like this is the lambda direction. We have two normal vectors that point, two inward pointing normal vectors that point up in the lambda direction. These two normal vectors will give us our change of variables that give our regions. And so the original integral can then be approximated as a sum over these regions. Okay, there's a potential issue with this, and that is that the method of region is subdividing the Newton polytope. So it can actually introduce new internal facets in the Newton polytope that were not previously there. And these new facets can introduce new spurious singularities that are not regulated by dimensional regularization. This makes sense. The sum of the regions needs to be regulated by dimensional regularization, but now we've introduced additional facets. There's no guarantee. And you can see this quite directly in the Lee-Pomeranski representation. Again, you get your Newton polytope. You work out your change of variables here. And now you will have some facets that are internal facets. They are new. You didn't see them before. And some of them will have this AF, this sort of offset, set to 0. And if this is the case, then this singularity here, if AF is 0, it cannot be regulated by dimensional regularization because there's no epsilon at all in this y. It's just a 1 over y, neat 1 over y. And so this gives you a procedure for knowing when you need analytic regulators, or in other words, when you need to modify the powers of your propagators by a small delta or add a small eta to it that will act as a regulator. So this is just a geometrical method of seeing when you need to do that. Just a simple example of how this works. If you have a polynomial like this, you draw its Newton polytope. Suppose that you get some new internal facet that lives on this blue line here. It goes through 0, so it will have an AF of 0, and this internal facet will lead to these spurious singularities. Just to say that PySecDec can just find these constraints, and it will print out these constraints for you and even suggest extra regulator exponents as well. So you can systematically do this. This expansion by regions is very useful because it allows you to expand your integral before integration. You can then compute the coefficients of that expansion numerically, and it allows you to scan over the space of the parameter that you've expanded in without having to do more numerical integration. You can also find that it's actually very much more stable in some cases. So when you have very large hierarchies, the numerical integration gets easier because you don't have these large scales in the numerical integral. And this just gives you a comparison of a numerical integral that we did versus its analytic result. You see that the error on the expansion by region result for large m²/s is much smaller than the standard PySecDec approach, and the time is dramatically less. Okay, I have been exploring with Inan et al. Bridges between this facet representation and the momentum representation, which I think is very interesting. But in the interest of time, I'm going to skip over this section, but feel free to ask some questions. I think there's a lot of interesting work here. In particular, we found a graphical method for identifying the region vectors. So you don't go via the Newton polytope at all, but you simply have a graphical method in a particular type of expansion that allows you to identify exactly which regions you will get just by looking at the graph. Okay, so I use my last few minutes, if you'll allow me, to flash some work in progress that might be of interest. Led by Vitaly, very much spearheaded. We're looking at the quark-initiated NF piece of TT Higgs. So this is an example of a 2 to 3 process that's certainly challenging and allows us to really check how well we're doing. It's a 5-point amplitude, and it depends on 5 kinematic scales and 2 masses. And it has 831 master integrals. So we have the reduction of this thing. Now, we've also been able to numerically evaluate this entire amplitude. So for the projectors, we use the Born amplitudes. For reduction, we do an on-the-fly numerical reduction for each phase space point, which is accelerated by this rat tracer tool of Italy. And for the integrals, we choose quasi-finite defactorizing integrals that have nice properties for PySecDec. And we're also investigating the series expansion of differential equation approach. So a first look at the phase space point, we have a target precision of 10⁻⁴. This is a particular phase space point. And we're actually able to evaluate everything, including the finite part of this thing, separated out by color structure and number of internal fermion loops. So this works. What's the catch? Well, the poles are fine. They're matching the subtraction formula. And we also have a cross-check thanks to the work of these people here who calculated these poles. For the finite part, we have around 16,000 phase space points or so. For a very good phase space point, so some of our best phase space points, on a GPU, we can compute the entire amplitude to the precision that we requested in around 3 to 4 minutes. So this is not too bad. This may be slower than an analytic result, but you can perhaps do physics with this. Unfortunately, when you get close to thresholds, of course, it gets harder. And we have some bad points where we get quite poor convergence. This is one of the worst points that we have. We get quite poor convergence, even after quite a lot of integration time. So it's certainly an open question, how to deal with the performance near these thresholds. It's one of the things motivating us looking at the series expansion of differential equations. And then, of course, this phase space is vast. So we need to be smart about how we actually sample it and not just use simple grids. And that brings me to my conclusion. Presented a few updates to PySecDec. It's a public tool. Everything that I spoke about, you have full access to. You can just download it onto your laptop or cluster and run it. I've shown you various processes that we've applied it to, and the first application to 2 to 3. And I also spoke a little bit about this method of regions. And one of the things that I'm exploring with Inan and collaborators is how this analysis that we perform generalizes to other types of expansion, for example, Reggie or massive particles or threshold or potential regions. And in particular, what happens when some of the coefficients of our monomial are negative or we have different signs in our polynomial. So thanks for listening.
So thank you very much for the talk. It is impressive how the improvements that you get. But still, you need typically for one single point in the phase space hours, right?
So I mean, as I
for
showed,
a reasonable accuracy.
For quite generic phase space points in this case, we're able to do it minutes on a GPU. Yes. It can happen that you have. And now I should say, of course, I mentioned it quite quickly here, but how long it's going to take depends very strongly on the basis that you pick, right? So we put quite some effort into finding integrals that are friendly to bisector.
Yeah, this is fine. But my question is now you have to integrate over phase space.
Yes.
So the total amount of time for a realistic phenomenological study will be years, right? Unless you are working in a cluster and all this stuff.
Which we are, but
so,
yes.
Oh, yes, you are. So my question is about your perspective for the future, because at some point we will reach some limit where you cannot go further.
Yeah, that's possible. I mean, there are always tricks in phase space. If you find a flat direction in phase space, then that's not really a direction you need to worry about, right? So it could be that just brute force sampling of the phase space is not the way to go. But it's true that as you add more legs, you will get a bigger and bigger phase space and you need more and more time for sure. And I mean, the method either needs to get faster at a considerable rate, or you hit a brick wall that you just can't pass.
Comment on this first and then the next question. Okay.
Just about phenomenology. So in the double Higgs calculation, we also had points that took 24 hours, but the way out was to construct a grid and interpolate between 5 space points. And once you can make sure that the grid is dense enough, also in difficult phase space regions, you can do phenomenology without waiting 100 years. And this is actually done. I mean, the experimentalists use this code and they use this grid. So that is the poor man's solution to the problem you mentioned.
You certainly don't want everybody rerunning this from scratch every time they need the result, right?
Since I'm here already,
Okay. Okay, so one question was in the beginning when you saw this reduction in time was about a full amplitude, an integral.
This was the particular integral that I showed you at the top, but it's indicative of the sort of reduction.
And was a physical point or a Euclidean point or what?
Good question. Probably physical.
Fine. Okay. In any case,
yeah.
That's one question. Now, sure. I'm also a bit about the contour stuff.
Okay.
What is really, because that's an important issue for us to compare. I mean, for the moment, we are not able to compare in the physical region, basically. So we did some comparison in the Euclidean region, but it will be nice also to have the physical region. So
sure.
What is your feeling that can we do a 5 point to loop stuff with your program?
As I showed, yes, depending on the integrals. But
no, without masses inside. I mean,
without masses inside. Of course, that's difficult for sector decomposition in principle because you can have more singularities.
More singularities, you mean what, in epsilon, the UV and different?
Yeah, I suppose so, yeah, for the sector.
But now the threshold is important.
Yeah. Okay, so what can I say about the contour deformation? I agree, it's a big issue, right? So it dramatically slows down our code when we need to go to the physical region. This is clear. If there was a way to identify how to somehow subtract this first, so that we're not having to deform around and go around these poles, this would be a real game changer for us, right? Then suddenly I would be very positive about the answer to your question. As it is now, we're making kind of incremental gains in that, an order of magnitude or something like that. But if you're talking about an integral where you have 100% error, it's not clear how many orders of magnitude we need to come down by before you start getting actual useful digits out of that integral. I would say this approach, the normalizing flow, it shows that you can get orders of magnitude.
Okay.
But it's
Here, okay, maybe it's too much technical, but you should start with some functions of X. I mean, what do you mean neural network using to find the function?
That's right.
You should start with what, a polynomial or what in X?
I mean, it's a normalizing flow. So yeah, I guess it's a type of products of matrices essentially. So it's like, I guess, functions of functions, something like this. Yeah. So that's kind of the answer.
So let me understand. You mean that if I have, so you tried this TT bar, okay, Higgs.
For this contour deformation, we tried it on these examples. For this.
No, I'm saying in your final thing, you start doing amplitude for TT bar Higgs.
Yes.
Why not doing things which are already known, let's say, okay, let's say, the
you mean
particle
things?
Yes, I mean Higgs plus or W plus BB bar massless. I mean,
Sure. So
I mean, it's more difficult for SecDec to do that, or it's more. I don't.
Maybe not, but to do these processes takes quite a lot of time because you need to find a good basis first. So we have 800 master integrals. We spend quite some time trying to find the good integrals in that space. So if we're going to spend that time, we don't really want to spend it on something that's already known because there's sort of less glory in it. In principle, you could try odd integrals from that and try to find good integrals in it, but it's not the same as a full amplitude.
But you see, this is a general remark for loop community.
Yes.
We have 10 years now, and we have results that nobody has cross-check results. I mean, in most of them. So, okay, I understand what you say. There is some calculation already, but it is important also to have some cross-check on this calculation.
Absolutely agree. Yeah.
That's a kind of, let's say, public asking the group to
I also agree with that, right? There are many cases. Yeah, a cross-check is important.
You briefly mentioned a way to illustrate the regions from the diagrams graphically without resorting to the Newton polytope slide 32, but it was a bit quick to understand.
Sorry,
maybe
of course, I didn't try to.
Maybe you could say a few words as well, so let's see it again.
Yes, okay. I could say a few words about the inspiration for it.
Okay.
So the inspiration for it is that the Landau equations give the necessary conditions for an integral to diverge. And the idea was to explore the neighborhood of a pinched surface. So explore the neighborhood of the solutions to these Landau equations. So you define Landau equations where you're looking at particular scalings of these things. And then you try to exploit this connection between the solution of the Landau equations and the regions. So we looked at a particular on-shell expansion. Okay, and with the method of regions, what you notice, so you're just looking at the Newton polytope on many different graphs, so you're seeing what you get here. What you notice is that you only get a very particular set of powers for your Lee-Pomeranski parameters. And these powers, you can guess that they correspond to hard, jet, or soft scalings of your propagators. In fact, with Schwinger parameters, you can show that these powers correspond to scalings of the propagators. And then you can guess what the actual momentum scaling is. So then you try to consider all the possible solutions of the Landau equation, and you search for ones that are scaleful. And so you get a bunch of constraints from the Landau equations and scalefulness, as well as this information. And you see that whatever graph that you're looking at, it needs to sort of be possible to partition the graph in this way for it to be a valid region. So you need to have jets, for example, the jets need to connect at a hard vertex. You can have soft, which can speak across these jets and so on. And so to all orders, it seems, you need to always have this structure, whatever order in lambda that you're talking about. And so noticing that structure, the idea was to come up with an algorithm to essentially construct this. So it's more or less a matter of building the graphs by building the jets by first looking at these graphs. And then once you have your jets, if you can build regions where you take one jet and another jet, and where a propagator belongs to both jets, it becomes a soft propagator. And in this way, with a few extra conditions, you can end up with this situation where you essentially work out different possible jet configurations for your diagram. And then, as well as having these as possible regions, you can also have regions where you have sort of an intersection of these.
Okay, so
Yeah.
okay, what you showed before is, of course, that's the general structure of what we call an SET1 factorization theorem.
Yes.
But I wanted to understand more specifically this graph. So the blue lines are
The hard lines
the hard ones, the green ones
are a particular jet associated with a
I see,
particular external momentum.
and the red dashed are the softs.
Exactly.
Okay, I see.
Exactly.
And
Yeah, I agree. I mean, we're essentially just rediscovering SCET, but
okay,
from
but
graphical
so
perspective.
for a what 6-loop
Yeah, this is a
diagram like
six.
this, you can simple rules to identify all the possible
yes.
regions. They have to be connected in some way.
Yes, exactly. So the hard needs to be connected and so on.
Yeah.
I mean, it needs to be compatible with this, right? And so with this set of rules, you can build up all possible graphs that are compatible with and then you can use the method, you can use the Newton polytope, you can write down the region vectors, and you can just validate that you indeed did get the correct thing. And so we did this, 3 legs at 5 loops, 4 legs at 4 loops, and then also this diagram. It really seems to work.
Okay, thanks.
I have a question. So did I understand you correctly that you do numerical reduction?
We do a reduction per phase space point. So you insert your kinematics first.
Yeah. So if you do numerical reduction, then you probably have a possibility to write down differential equation for this numerical.
Yeah.
Then why do you insist on integration?
Rather than just solving the differential equations through, say, series expansion. Yeah,
Well,
I mean,
you can solve them in
or numerically with it, directly. Yes. So, I mean, to say the approach that we're investigating is this diff-exp approach. So you pick a phase space point and you leave one parameter free, let's say. Yeah, exactly. So it's possible, right? It could work. If you just pass this directly to the diff-exp package, it's not a big fan. Maybe that's because we're stupid users. Maybe it's because it's quite complicated. I don't know. But it's something that we're trying. So I agree with you. That's a method that we could certainly try. Yes.
This is actually, intrinsically more stable in a certain sense.
I don't know. I mean, diff-exp also takes a lot more time. The series solution also takes a lot more time as you approach a threshold, right? So, I mean, as you get close to the singularities, you need more and more little hops and deeper series expansions and higher precision and so on. So you also see these thresholds increasing the time.
But can't you control better what you're doing?
Maybe. Yeah. This is why we attack the problem with all the tools we have at hand.
And in this, I don't know, 3-4 minutes per point.
Yes.
This is numerical reduction plays no role. I mean, it's just epsilon.
So this is actually not included in this time because it's done offline to generate the system that we're integrating, but it's order minutes per phase space point.
And if you keep one parameter free, then what will
Yeah, that's with one parameter free. Yeah.
Udo first. Yeah.
Hi, Steven. I have a question on the Newton polytope that you showed. Usually from the volume of the Newton polytope, if the representation of the integral is okay, you should get the number of master integral is the same as the number of master integral. Do you ever check if this is the case or if sometime it fails?
I'm aware of this. I've never played with it at all. Yeah, we don't have it implemented, but it's true. We probably have all of the framework to do it. Yeah. I guess one thing that it maybe doesn't capture so well is when you have master integrals related by symmetries, right? It can overcount. It's kind of, you have to mod by the number of symmetries. But yeah, we didn't really investigate it.
Yeah, I was wondering about the jet soft hard factorization that you were discussing before with Martin. By the way, the level of power counting, this goes way back, right? This is like Libby Sturman and companies and other people. However, so you say consider possible solution to the Landau equations, and I guess you mean in the physical region. So yes, very good.
Yes,
because of course it would be much more complicated. And next, I was wondering whether you are allowing for masses, or is this all massless? I mean,
this is all massless.
All massless.
So you have all massless off-shell external legs, and then you're taking the limit that they go on shell, which unveils the kind of infrared structure of the thing.
Because if you had masses, you would still have configurations that would be logarithms instead of singularities. But you are massless now, which
is, so they take this as the first step in that direction.
Sure. No, this is fantastic. I mean, and then I had one more thing, but I forgot. So
yeah, too little coffee.
Nice talk, Steve. So since you have control on the different sectors by triangulating the Newton polytope, I was wondering whether there is any prospect in tropicalizing these integrants.
Yeah. So you're right that the tropical sampling is really closely related, right? Because you start again from the Newton polytope. And then rather than trying to factorize the singularities, you just multiply by a tropicalized version and divide by the same thing, and then sample according to that. The triangulation is a technicality, but it's a problem, I agree, because what it can do is break symmetries of your integral. And at the moment, for our triangulation, we simply just take what the mathematicians give us, right? They provide a tool, it triangulates, very happy. But in general, we would like to find, say, the minimum number of triangles, or maybe there is another property that's a good triangulation. And this is an NP hard problem. So unless there's something special about our integrals that we can see, then our triangulation a little bit breaks the beauty of this structure. And it's true that a tool like FineTrop actually avoids it, right? By just looking at this extremal vertices. So in short, I'd like to find a better triangulation. I can't do better than what the tool provides to us at the moment.
And if I can ask a subsequent question, does Bisector rely on other sources to do this triangulation for the different sectors?
Rely on
other sources for?
Yes, Normaliz. It uses a package called Normaliz. I think there's another package called QHull as well that's used by Fiesta for similar things. Yeah.
Thanks.
Yes.
Very quick question about like some of the speculation regarding how to extend this method when you have different signs for these CIs. If you can comment and say something about that.
Yes.
Which I guess is related to Glauber regions, right, where you don't get singularities in the boundaries. And,
right. Exactly. Okay. So when you get different signs, what you would ideally like to do is find, ideally, I would like to find a change of variables that allows me to split up my integral into different regions so that I don't have different signs in these different regions. That could be overdoing the job. It's not necessary just because there are different signs that there's really a solution that leads to a scaleful integral inside. So that's the first question. In this work that I'm doing with Enan on this Reggie limit, we found an algorithm to kind of filter diagrams where they could potentially have this problem due to the signs. And we've kind of identified a few bad guys that start at 3 loop actually that have this. And there, when you look at it in this particular limit, you get it factorizes very, very nicely. And so we're exploring different changes of variables there that allow us to then use the geometrical methods to find those regions. And one thing that I can say is, based on the change of variables that you do, you can introduce a lot of extra regions that will cancel in a very strange way. But there are changes of variables that seem to introduce very few additional regions and indeed expose exactly this kind of facet that is hidden at the moment. Yeah.
Thank you.
Yeah, still a question on the unlucky lattices.
Yes.
I mean, yeah, you show that you see them only when you have a very large lattice.
You see the fluctuations always, but when you have a large lattice, you already have quite high precision.
Yeah.
So it can fluctuate a lot higher.
And you say that you don't know the reason. I mean, you cannot guess even.
I really don't understand it. It seems, I mean, our functions should obey the rules that they use to derive the scaling of this lattice rule.
Okay.
I don't see anything special about this sector that is not there in that sector. They're very similar objects to me, but there's something I'm not seeing. And I spoke to the mathematicians who came up with this component by component construction, and I tried to explain.
And in practice, in your calculation of the amplitude problem, how is a big problem? So in TTX, I mean, the fact that you have this.
I mean, if you're
in practice,
suppose that you're targeting, say, to get below 10 to the 9, right? If you pick this lattice, you will get there. If you pick this lattice, you will be very, very, very far away from it. You will then probably guess that you need a much larger lattice. So maybe you compute this lattice, which is 10 times bigger. So then your 3 or 4 minutes become 30 or 40 minutes, purely because you were unlucky.
But you do check iteratively, I mean.
Yeah, I mean, what our algorithm does.
You do the calculation many different times.
We'll start with a lattice. Based on the precision of that lattice and a guess of this scaling, we will jump to a lattice that we think gets us to the precision that we actually want. And then we will jump to another lattice that we think gets us to the precision we want. Yeah. But, you know, you can happen that you're here and then you jump here and you got no improvement and you spent 1,000 times.
Yeah. Okay, so the time can become exponentially large. And just last question on GPUs. You say that you port to GPU only a part of your calculation that is summing results.
No. The sampling is done on the GPU.
Okay, it's also
so that's been implemented for a long time.
Yeah.
But what we used to do was we used to sample phase-space points and we would partially sum them, and then we would transfer blocks of partially summed results back to the CPU.
Yeah.
Now we actually do the full reduction on the GPU, so it retains a number.
Okay, and the other question is, how do you deal with the fact that you need really a very high, I mean, a lot of decimal cipher, I mean, really high precision with GPUs, because normally GPUs will run real star4 calculation.
All of this is done, everything that I showed you is done in FP64, so double.
Okay.
We don't
double, so you cannot go up over. I mean, I don't know in PyStack, but my experience, sometimes double precision is not enough.
Yeah, in principle, you can find integrands where you would need to sample the integrand itself with quadruple precision in order for the thing to converge. We try to avoid that, but it can happen. But this is part of, I guess, picking your integrals and doing some experiments to understand how different integrals are behaving. Okay. Yeah, but it can happen.
You cannot think to a splitted calculation where, for instance, where you need the quadruple precision, you use CPUs, and when you just need the lower precision, you use GPUs. You are not yet at that level.
We're not doing that. Yeah. I did implement for CPUs this boost multi-precision. So in principle, you can sample your integrand with any precision that you want on a CPU, but it's much slower. I mean, it's really a lot slower once you leave hardware. So for very simple integrals, if you're really sure you want a lot of digits, fine, you can pay the price. But for the type of stuff we're doing here, you don't want to be sampling, tens of thousands of sectors in that precision. It's too slow.
Thanks.
Okay, myself. Okay, sorry. This question, I follow the question by Kirill. I mean, when you do the reduction, you say there, go back to this transparency with Ratatar. It's okay, Ratracer. First of all, your amplitude is analytic, no?
Initially, yes, you have the full analytic amplitude, unreduced.
Sorry?
Unreduced. You have the unreduced amplitude. You pick a phase space point.
So you have an expression of the amplitude. It's up.
Yeah, I mean, just the sum of this. Yes.
Okay.
Yeah.
Then some coefficient with, so what do you think is tensor integrals, or it's in Feynman parameter space?
No, I mean,
already?
you write it in terms of integral families with potentially inverse propagators or dots, right? And then you have your amplitude analytically like that, but it's not master integrals. It's just, thousands of random integrals written based on your choice.
And then you go.
Then you pick a phase space point, like a rational phase space point or something like this. You plug that number in, and then you reduce to the master integrals only on that phase space point. So you only know the coefficient.
You mean you use an APB program to reduce to master integrals?
Yes. Yes. Yeah.
Why you don't integrate, let's say, immediately in next space?
I mean, there are very many integrals.
Okay.
They have no nice properties whatsoever. So the numerical performance is
and this physical point is always to be rational, somehow irrational, or can.
I mean, you can do this in floating point, but you can lose precision when you do this reduction, right? So the thing to do is to find a rational number that's close to the floating point.
Okay, great discussion. So we can continue maybe offline. Is that okay, or any urgent? No? Okay. Yeah.
Shall we just keep going until coffee?
That's right. Okay, so let's thank Stephen again.
Okay.